Jai Hind everyone. Myself Dr. Sharma from Ajay Kumar Garg Engineering College, Ghaziabad. I'm taking engineering physics and subject code of my subject is KS101T and KS201T. In first semester it is KS101T and in second it is KS201T. The topic which today I am taking for discussion, that topic belongs to relativistic mechanics, and the topic which I am taking today for discussion, that topic is basically Lorentz transformation equations. This is my basic topic for discussion. But in order to understand Lorentz transformation equations, first we have to understand some basic concepts which are related to relativistic mechanics. So when I'm saying mechanics means that particular branch of physics where we are dealing with motion of the objects, where we are describing moving objects. And whenever we have moving objects, whenever we are dealing with mechanics, we can classify this particular branch of mechanics in two categories or in two groups. And that depends upon the speed with which that particle is moving. So what I'm trying to explain here, that whenever we have a moving particle, in order to describe the motion of that particle, we have two branches in which we can describe the motion of that particle. The first one is known as classical mechanics and the second one is known as relativistic mechanics. And the branch which the topic which I have taken here, that belongs to relativistic mechanics. So let's try to understand that what is the basic difference between our classical mechanics and relativistic mechanics. So I'm describing the difference between these two branches just by a simple equation. If we have a moving object and if the speed of that object is very, very small with respect to c. Here the c is representing speed of light. So if the speed of object is very, very small with respect to c, then we will use classical mechanics in order to describe motion of that object. So if you want to describe the motion of such type of objects, then you will take classical mechanics, which is also known as Newtonian mechanics. Means we will simply use Newton's laws of motion to describe the motion of such type of objects. So that is our classical mechanics. The second one is when we have a moving object and that object is traveling with a speed comparable to speed of light. So this is the second case. Now again you have a moving object, again you want to describe the motion of that object, but now this v is comparable to c. So in order to describe a motion of such type of object, you cannot use classical mechanics. Then we have a different branch, which was proposed by actually Albert Einstein in 1905. And that branch is known as relativistic mechanics. So basically the topic of today's discussion, that is also based upon relativistic mechanics. So our topic of today's discussion is Lorentz transformation equations. So now, before going into detail of Lorentz transformation equation, first I would like to highlight frame of references here. Suppose you have this object and this object is kept somewhere in this particular room and you want to describe the position of that object. So if you want to describe the position of this object, then what you require? Just think what you require to describe position of this object. In 3 dimension, in order to describe position of this object, you require 3 position coordinates, that is x, y and z. So in order to describe the position, 3 position coordinates are required. And in order to describe motion, 1 additional coordinate, which is known as time coordinate, that is also required. So in order to complete description of motion of any object, a set of 4 coordinates are required. In that particular set, we have 3 position coordinates and a time coordinate. So that is also written over here, that in a frame of reference, basically we have a combination of 4 coordinate axes. Out of those 4, 3 are position coordinates and 1 is known as a time coordinate. And this particular combination x, y, z, t, this will describe the motion of any object in a particular frame of reference. In order to describe motion of any object, we always preferred unaccelerated frame of references, or you can say inertial frame of references. Basically, the frame of references are of two types. As you already know from your previous classes, that frame of references are of two types. One is known as inertial and the other one is known as non-inertial. And the beauty of inertial frame of references is that laws of motion, they will remain in the same form in inertial frame of references. So whenever you want to describe motion of any object, we will always prefer inertial frames. So whenever you will describe motion of any object in any particular frame of reference, then we will always prefer inertial frames. So since I am going to describe Lorentz transformation equations, so whenever I will refer a frame of reference in my topic here, then those frame of references are basically referring inertial frame of references, or you can say unaccelerated frame of references. Now, before going into Lorentz transformation equations, which is actually the topic of today's discussion, first I would like to highlight these GALLILEAN transformation equations. Now, before understanding these equations, first we will try to understand that what is the meaning of transformation equation. What is the actual meaning of this term, transformation equations? Now, in order to understand, you have to understand this particular figure here. So, what we have here, we have two inertial frames. This is our first inertial frame and this one is the second inertial frame. This frame, the first one, that is 1, that particular frame is inertial frame and this particular frame is at rest, and we have represented this frame by S. So, S is our first inertial frame which is at rest, and there is an observer who is sitting in frame S. Now, suppose the observer who is sitting in frame S, that observer want to describe any event. Now, in order to describe any event with respect to this inertial frame, what we require? We require a set of 4 coordinate axes, as I have already mentioned. So, we require 3 position coordinates and a time coordinate. So, with respect to S, for that particular object, for that particular event, we have a set of 4 coordinates, that is X, Y, Z and T. Now, see, there is one more inertial frame here, another inertial frame, that is frame S dash. And in this frame S dash, another observer is sitting and that observer is O dash. Now, you have to see this particular point very carefully, that this frame S dash, now it is not at rest. This particular frame is moving along x-axis. You can see this particular arrow. This arrow is representing the direction of motion. So, your S dash is moving along x-axis. The direction of motion is only along x-axis. No movement of this frame along y-axis or z-axis. It is moving only along x-axis. So, S dash is moving along x-axis. And one more point, this S dash is moving with this constant velocity along x-axis. Now, these equations, GALLILEAN equations, these are applicable only in classical mechanics when V is very, very small with respect to C. So, your frame S dash that is moving with this V, which is very, very small with respect to C. So, the event which was recorded by frame S, the same event is also recorded by S dash. Means 2 observers are there. One observer is sitting in frame S, that is observer O, and another observer that is sitting in frame S dash, and that observer is O dash. And both the observers are recording the same event. Let the coordinates with respect to S dash are X dash, Y dash, Z dash and T dash. These are the coordinates with respect to S dash, and the coordinates with respect to S are X, Y, Z and T. So, same event recorded by 2 different observers. If you can convert the coordinates of one inertial frame, if you can transform the coordinates of one inertial frame into the coordinates of other inertial frame, then those equations which will correlate those coordinates, those equations are basically transformation equations. I hope this point is clear to you. So, the meaning of transformation equation is, what you have to do, you have to transform the coordinates of frame S in terms of coordinates of frame S dash. Means, if you can write x dash in terms of x, y dash in terms of y, z dash in terms of z, and t dash in terms of t, then those equations which will correlate these coordinates, those equations are basically your transformation equations. So as you know, there are 4 coordinates, x, y, z, and t. You have 4 different coordinates in frame S dash, x dash, y dash, z dash, and t dash. So 4 coordinates are there. So there will be 4 equations which will transform the coordinates along x-axis, along y-axis, along z-axis, along for that time coordinate. So 4 transformation equations will be there. 1 for x-axis, 1 for y-axis, 1 for z-axis, and 1 for time coordinate. But as I have mentioned earlier, that we can classify mechanics in 2 groups. One is classical and the other one is relativistic mechanics. So the equations which I have mentioned over here, these equations are applicable only in classical mechanics. So when you have this particular case, when V is very, very small with respect to C, then you have 4 equations which are known as Galilean transformation equations. So these equations are x dash is x minus vt, y dash is y, z dash is z, and t dash is t. Now how you are getting those equations? I am giving you a small description of this because our topic of discussion is basically Lorentz equations which are applicable in relativistic mechanics. But before going into detail of those equations, you have to understand that how you are getting these equations. So suppose your both the observers, that is S and S dash, initially both the observers, they are coinciding with each other. Means your frame S and S dash both are overlapping. When both are overlapping, then O and O dash both are present at same position. At this position, your both observers are there. Now S will remain in the same state, but S dash will move along x-axis. And let this position of S dash is after time t, means this particular displacement, this is after time t. So if after time t, this is the displacement, then you can write this displacement between both the frames either as Vt or Vt dash. Why I am writing Vt or Vt dash? Because initially when both the observers, both the frames are coinciding, at that point, if 2 similar type of clocks are there with O and O dash, both will keep same time. And if after a certain time you are recording this particular event or the position of S dash, then that time is either T or T dash. So this displacement can be written as Vt or Vt dash, both are same. So this is the displacement after time T or T dash. And with respect to frame S, let this is your event is occurring at this position. Then with respect to S, this distance is x. And with respect to S dash, this distance is x dash. Now you can easily see from this diagram that x dash is basically x minus this particular term. So x minus Vt. So this x dash is x minus Vt. Now you can see in equation number 1, on the right hand side, all the terms belongs to frame S. And on the left hand side, all the terms belongs to frame S dash. Means you have converted the coordinates of one inertial frame in terms of coordinates of other inertial frame. You have written x dash in terms of x. Along y-axis, since there is no motion of this S dash along y-axis, so this particular distance, you can write it as y or y dash. Both are same. It means the transformation equation along y-axis is y dash equal to y. No change along y-axis. Similarly, along the third direction, which you can't see here, but you can imagine, along the third direction, since no movement of S dash along z-axis, so your z dash is also z. So these equation number 1, 2 and 3, these are the 3 transformation equations for position coordinates x, y and z. And for time, since you are recording time after initially when both the observers are coinciding, both the clocks are taking same time, t is t dash equals to 0. If you are taking observation after 5 seconds, then according to your clock, which is kept with the observer O as well as the clock which is kept with O dash, both the clocks will give same time. It means there is no change in time in classical mechanics. So your fourth equation is t dash equals to t. So these are 4 equations, 1, 2, 3 and 4. These are Galilean transformation equations which are applicable in classical mechanics. So if these equations are clear, then we can easily understand the transformation equations for relativistic mechanics with a slight twist. So basically, these Lorentz transformation equations or relativistic mechanics that is based upon the special theory of relativity, which was proposed by Albert Einstein in 1905. So relativity is incomplete without the postulates of special theory of relativity. So I'm just referring those 2 postulates of special theory of relativity on which the entire relativistic mechanics is based upon. And whenever I will describe any event or any law in relativistic mechanics, that will be applicable only for inertial frames. I'm referring only inertial frames here. So this special theory of relativity, it is based upon 2 principles or 2 laws. The first one is law of equivalence, which means if a particular law, if a particular equation is applicable in one inertial frame, then it is equally applicable in all inertial frames. You can take an example. Suppose you have 2 inertial frames S and S dash. Suppose in frame S, you have an equation y is equal to 3x plus z plus 5. Then there will be a similar type of equation in another inertial frame. Means all the laws of physics are equally applicable in all inertial frames. If one particular law, if one particular equation is applicable for one inertial frame, then you can say that that equation, that law will be applicable for all inertial frames. This is our principle of equivalence or law of equivalence. The second one on which this special theory of relativity is based upon, which is the main idea behind relativity, and according to that particular principle or law is law of constancy of speed of light. According to this, the speed of light, which is represented by c, that is a universal constant and it is having a constant value in all inertial frames. And I am 100% sure that each and everyone knows the value of speed of light, which is 3 into 10 raised to power 8 meter per second. So these are the 2 postulates which are actually the heart of special theory of relativity, and our Lorentz equations are also based upon these 2 postulates of special theory of relativity. We will use these postulates to get those Lorentz equations. So now our main topic, Lorentz transformation equations. Now in order to understand these equations, again you have to take 2 inertial frames. So what we have here? We have 2 inertial frames. So, as you have taken 2 inertial frames in a Galilean transformation equation, you have a similar type of case here. 2 inertial frames are there. Suppose the first one is your frame number S and the other frame, second one is S dash. These are your 2 inertial frames S and S dash. This S and S dash, now you have to understand this particular concept of Lorentz equations from the starting. So what we have, initially S and S dash, both are coinciding with each other. When t is t dash equals to 0, this is the initial point. What is this t and t dash? You can understand it like this. This observer O is having a clock C1. And a similar type of clock is there with observer O dash who is sitting in frame S dash. So what you have 2 inertial frames. One is S and other one is S dash. 2 observers are there. One is sitting in frame S and other one is sitting in S dash. This observer is O and this one is O dash. They have similar type of clocks, C1 and C2. These two clocks, they are recording same time when T is T dash equals to 0. Means the time of both the clocks is matching when T is T dash equals to 0. Now this S will remain in the same state, that is state of rest. But this S dash, S is at rest, so that is an inertial frame. Now this second frame, which is your S dash frame, this frame is moving along x-axis. This frame has started moving along x-axis with a constant speed and it is moving along x-axis. You know, when a particular frame is moving with a constant velocity, then acceleration is 0 and that particular frame is your inertial frame. So it means both the frames are inertial frames. S is inertial, S dash is also inertial. S is at rest, initially both are at rest. But S will remain in the state of rest forever. But S dash, it is moving along x-axis with the constant velocity. And you have to remember that these equations, mostly whenever we will apply these equations will be applicable in relativistic mechanics when this V is comparable to C. Means this particular frame S dash is moving with a very high speed which is comparable to speed of light. But I am not saying that these equations are not applicable when V is very, very small with respect to C. The beauty of relativistic mechanics is when we will apply these conditions, automatically all the results of relativistic mechanics will approach the results of classical mechanics. That we will understand at the end. But right now you have to remember, this is at rest, this will remain in the state of rest. This one is moving with the constant speed, which is comparable to C. Only then you will apply relativistic mechanics, only then you will get these equations. Now, there is an event which is recorded by both the observers. So let this point P is that particular point where the event is happening and we are recording that event with respect to O or as well as with respect to O dash. Let the set of coordinates with respect to S are X, Y, Z and T. These are the coordinates with respect to frame S. And the coordinates for the same event with respect to S dash are X dash, Y dash, Z dash and T dash. So obviously two different observers are there, two different inertial frames are there, both are recording same event. So you will have two different set of coordinates. One is X, Y, Z and T, that is the first set with respect to S, this is with respect to S. And the second set is with respect to S dash. So you know what is the meaning of transformation equation, as I have already explained. Transformation equations means you have to correlate the coordinates of one inertial frame in terms of coordinates of other inertial frame. Means you have to transform X in terms of X dash, Y in terms of Y dash, Z in terms of Z, T in terms of T dash. And as you can see here, 4 coordinates are there. So there will be 4 equations as you were getting in case of classical mechanics, Galilean equations, 4 equations were there. So similarly you will get 4 equations here. But the difference, that is mainly because of this particular factor. This factor is going to change the entire scenario. Because of this particular condition, there is a change in those equations, and once you will get that change, once you will get those 4 Lorentz equations, you will see that all the parameters like length, mass, time, everything will change in relativistic mechanics. As you know, in classical mechanics, everything is absolute, nothing is affected by motion. But that is not the case of relativistic mechanics. In relativistic mechanics, whenever an object is traveling with relativistic speed, mass is affected by motion, length is affected by motion, even time is affected by motion. So all these changes are because of this particular factor. So now we will try to understand that how this factor is changing those transformation equations, why we are getting that change here. So in order to understand that, basically Lorentz proposed a new transformation for this particular condition. So what was proposed by Lorentz? Lorentz proposed that measurement along direction of motion. So you can see what is the direction of motion here. Direction of motion is along x-axis, no change along y or z-axis. So according to Lorentz, measurement along direction of motion. So what is the direction of motion? Direction of motion is x-axis. So measurement along direction of motion in one inertial frame. So you can take any frame, you can take S, you can take S dash. So measurement along direction of motion. So when I'm saying direction of motion, then it is very much clear that we are referring x-axis here. So measurement along direction of motion in one inertial frame is directly proportional to measurement in another inertial frame. It means when we are talking about the measurement along direction of motion, we are referring x or x dash. So in classical mechanics, or simply without any relativistic effect, you know that x dash, it is actually x minus vt. That is the case of your classical mechanics. But in relativistic mechanics, you have a different condition, you have a different scenario, which was proposed by Lorentz. And according to Lorentz, actually this x dash is not x minus vt, but this x dash, it is proportional to x minus vt. Means the measurement along direction of motion in one inertial frame. If I am taking x dash, then it is an s dash frame. So measurement along direction of motion in one inertial frame is directly proportional to measurement in other inertial frame. So instead of x dash equal to x minus vt, we have x dash proportional to x minus vt. This is the main idea. If you are dealing with classical mechanics, then simply x dash will be x minus vt, and that is very much clear to you. According to simple algebra, x dash will be x minus vt. But now in this particular case, according to Lorentz, this x dash is proportional to x minus vt. And you all know, if you will remove proportionality sign, then what we will get? We will get a constant. And we have taken that constant as gamma. And you know, everything is known in this equation. This x dash, that is a parameter along x-axis in frame s dash. And rest on right hand side, all the parameters belongs to s frame. The only difference is, there is one unknown constant there, and that constant is gamma. If you can find the value of gamma, then you have transformation equation. You have the transformation of x in terms of x dash. So now our main idea is to find this gamma, and once the value of gamma is known, you have your transformation equation. So now we will see that how to find the value of this gamma. And in order to find the value of gamma, we are going to use our two postulates of special theory of relativity. We will use those postulates and we will get the value of gamma. So this was the proposal by Lorentz, which I have already explained. Now using this concept, we will get Lorentz transformation equation. So what I mentioned, that x dash is not equal to my x minus vt, rather x dash is proportional to x minus vt, and once proportionality sign is removed, we are getting this constant gamma. Now how to find this gamma? What is the idea to find this value of gamma? So first we are going to use our first postulate of special theory of relativity. I hope the first postulate of special theory of relativity is clear to you. According to first postulate of special theory of relativity, if a particular equation, if a particular law is applicable in one inertial frame, then that law is applicable in all inertial frames. So you can see this equation, the equation which I have highlighted here. According to this equation, x dash is gamma into x minus vt. Means this equation is applicable in frame s dash. You know, s is also an inertial frame. If you can write x dash like this, in s dash you can write x dash like this, then according to first postulate of special theory of relativity, we have a similar type of equation in frame s. If for S dash we have this equation, then according to principle of equivalence, we have a similar type of equation in frame S. What will be that equation? X dash equals to gamma. That equation will be X dash equals to gamma. Sorry, I'm writing the same equation. Equation will be X equals to gamma X dash plus Vt dash. Just see these two equations. The first one, this equation is for frame S dash and this equation is for frame S. So if you have this equation for frame S dash according to Lorentz transformation, then according to principle of equivalence, you have a similar type of equation for X also, which is gamma X dash plus Vt dash. Now we have to use these two equations to find the value of gamma, which we have done in the next slide. You have equation number 1, X dash equals to gamma X minus Vt, and as I have mentioned, we have a similar type of equation for X, which is gamma into X dash plus Vt dash. If in both the equations, that is in 1 and 2, if gamma is known, then the problem is solved. If gamma is known, then we have transformation equation. So what we have to do, we have to find the value of gamma. So in order to find the value of gamma, now we have to use our second postulate of special theory of relativity. So both the postulates of special theory of relativity are utilized to get those equations. So now how you are going to use second postulate? In order to understand, again, we are referring this same slide. So you can understand it like this. Initially, when t is t dash equals to 0. At this particular point, suppose you have a light source here. When t is t dash equals to 0, when t is t dash equals to 0, you know O and O dash both are overlapping, both are present at same position. At that point, when both the frames are overlapping, you have a light source at this particular position. So a light source is there at O or O dash. Then that light source, that will give you the light radiations. You have a light source at this position. So if you have a light source, then that light source will give you the light along all the possible directions. Means you will get the light along x-axis, you will get the light along y-axis as well as z-axis. And if you have light, then light will travel with speed of light, that is c. Means you have light rays which are traveling with c in frame S. And you know S dash is also an inertial frame. And according to second postulate of special theory of relativity, speed of light is same in all inertial frames. Means if the light is traveling with c in frame S, then light is also traveling with same speed in frame S dash. I am repeating what I have told you here. You have a light source which is kept at the origin. Origin means when t is t dash equals to 0, both are overlapping. A light source is kept over this particular point. Now this light source, that will give you the light along all possible directions. Light will travel with speed c in frame S, which is an inertial frame. S dash is also an inertial frame, and according to second postulate, light will travel with the same speed in frame S dash. So now it is clear that light is traveling with same speed in both the frames according to second postulate of constancy of speed of light. Now suppose light has traveled a distance x in time t in this frame S, and light is traveling a distance x dash in time t dash in frame S dash. I am taking only direction of motion here. So along x-axis, if light is traveling this distance in time t with this speed, then x will be equal to, you have distance x, you have that speed with which light is moving, and the time taken is t. So it means if light is traveling x distance in time t in frame S, then this x can be written as c into t. That is your first equation in frame S for those light rays which are traveling along x-axis. In frame S dash, since light is traveling x dash in time t dash with same speed c, so you have x dash as ct dash. So what you have? You have in frame S x as ct, and in frame S dash you have x dash as ct dash. So now what we are going to do? We are going to substitute the value of this x and x dash in our equation number 1 and equation number 2. So your x is ct here and x dash is ct dash. So if you will substitute x as ct and ct dash and simplifying equation number 1 and 2, what you will get? You will get ct dash is equal to gamma into ct minus vt. This is from 1. And from 2, your ct will be equal to gamma ct dash plus vt dash. Right? These are two equations. You have to simplify these two. So in order to simplify, just multiply these two. So if you will multiply these two, you will get c square tt dash gamma square tt dash into c square minus v square. These equations are already solved in next slide. So I'm just giving you a small idea about the solution of these equations. So gamma square is equal to c square upon c square minus v square. Further simplifying this, you will get this most important factor of relativistic mechanics, which is gamma. So your gamma is 1 upon under root 1 minus v square upon c square. So this gamma, which is calculated over here, this gamma is the main culprit in relativistic mechanics. This gamma is the main ingredient which is going to change each and every parameter of relativistic mechanics. You know, mass is affected by motion in relativistic mechanics, and that changes because of this factor. Length is affected by motion, and that change in length is also because of this factor. Time is also affected by motion, so that change in time is also because of this factor. So this gamma is the main factor. So you have the value of gamma, which is 1 upon under root 1 minus v square upon c square. So problem solved. Gamma, we have gamma now. Just substitute the value of gamma and you have your transformation equation. So as we have already solved this, so we have gamma as 1 upon root 1 minus v square upon c square. And we know that our x dash, that was equal to gamma into x minus vt. So we have substituted the value of gamma here, and after substitution, we will get our transformation equation along x-axis, and that equation is x dash equals to x minus vt upon root 1 minus v square upon c square. That is the transformation equation along direction of motion. And you can see from this previous slide that direction of motion is only along x-axis. So it means the change is only along x-axis. There is no movement of this s dash along y or z axis. So because of that reason, next two equations, that is next two transformation equations, are in the same form. That is no change along y-axis. Y dash is y and z dash equals to z. You can understand it like this. If the direction of motion is of s dash is along y-axis, then this parameter will not change. This x dash will be x only. Y dash, in that case, if the direction of motion is along y-axis, then y dash will change. That y dash will be y minus vt upon root 1 minus v square upon c square. Z dash will not change. So the change will take place only along direction of motion. So these are the three transformation equations for position coordinates. But now one more coordinate is left, which is your time coordinate. So we have to see that how time is affected by this motion, how time is affected by this particular factor of gamma. So in order to find that change in time, what you have to do, you have to refer your equation number 1 and 2. You know, from equation number 2, you have x upon gamma equals to x dash plus vt dash. You can see your equation number 2. From that equation, I am writing this. And you also know that your x dash is gamma x minus vt, right? Plus vt dash as it is. Vt dash. So basically what you have to do, you have to find the value of T dash in terms of T. So I'm just simplifying this. If you will simplify this, it will be T dash will be gamma into T minus Vx upon C square. How you are getting this? Give me a second. I will explain that how you are getting this. You have, sorry, just a second. You have x as gamma, x dash, give me a second, plus Vt dash. It is your x upon gamma minus x dash equals to Bt dash. Then further you have x upon gamma minus this x dash is gamma, x minus Vt equals to Vt dash. Our aim is to find T dash. So I'm simplifying it for a T dash here. So your T dash is x upon gamma into V minus gamma x upon V plus gamma into T. Now what we have to do here? We have to write it like this, gamma T. I have written it as first term. And from these two, I have taken minus gamma x upon V common. So I'm taking minus gamma x upon V common. If I'm taking this as a common factor, then you can see here the remaining factors are 1 minus 1 upon gamma square. So now what you have? T dash is your gamma T minus gamma x upon V and this 1 minus 1 upon gamma square. You already know what is the value of gamma square. So if you will simplify this, then this factor in the bracket, that will give you only V square upon C square. And if you will substitute this, then what you are going to get? You are going to get gamma T minus gamma xV upon C square. And in these two, you have gamma as common factor, T minus Vx upon C square. And you already know what is the value of gamma. So you have to simply substitute the value of gamma here. So what you are getting? You are getting your T dash as gamma into T minus Vx upon C square. You already have the value of gamma here. Just substitute the value of gamma. You will get T dash is equal to T minus Vx upon C square upon under root 1 minus V square upon C square. So now you have a set of 4 equations. Equation number 5, 6, 7 and 8. 5, 6, 7, they are representing position coordinates and 8 is your time coordinate, right? So these are your 4 Lorentz equations. This particular set of 4 equations is known as Lorentz equations, right? Now, one point I would like to highlight here. In these equations, you know, when this, if you will take this particular condition, when V is very, very small with respect to C. If V is very, very small with respect to C, then x dash, which you know, x minus Vt upon under root 1 minus V square upon C square. If this factor is very small with respect to C, this factor is taking negligibly small value with respect to 1. So this entire factor in the denominator, that will give you 1 value. It means x dash will be x minus Vt. So under this condition, your x dash is x minus Vt. Your y dash is already y, no change in this. Z dash is already z, no change in that. And the last one, time transformation, that is t minus Vx upon C square upon root 1 minus V square upon C square. You know, under this condition, this denominator will give you 1. So denominator is already giving you 1 value. And this V is very, very small with respect to C. So in the denominator, you have C square. It means this factor is having very, very small value, which is approaching to 0. So this factor will take 0 value. You can neglect it with respect to t. It means under this condition, t dash is t. So under classical condition, x dash is taking x minus Vt value. Y dash is y, z dash is z, and t dash is t. And if you will see carefully, then these 4 equations are actually Galilean transformation equation. Means under classical conditions, all the results all the equations, Lorentz transformation equations, will approach to Galilean transformation equations. Means we are also getting the results of classical mechanics from these Lorentz equations. And these 4 equations, these are actually the inverse of Lorentz equation. Means I have written x dash in terms of x. You can also write x in terms of x dash like this. X equal to x dash plus vt dash upon this, y is equal to y dash, z equal to z dash, and t is equal to t dash plus vx dash upon c square upon under root 1 minus v square upon c square. So these are the inverse equation. So we can conclude our lecture like this. Lorentz equations are basically a set of 4 equations, and these Lorentz equations are mainly, these equations are applicable when V is comparable to C. But these equations are equally applicable when V is very, very small with respect to C. So that is the beauty of your Lorentz equations, and these Lorentz equations are responsible for all the changes in different parameters in relativistic mechanics. So that's all for today. Thank you so much.